Durante todo el taller contaremos con interpretación simultánea español-inglés, inglés-español. Pueden seleccionar el idioma de su preferencia en el menú horizontal inferior. Esto va para aquellos participantes virtuales. During the entire workshop, we'll provide simultaneous translation Spanish-English, English-Spanish. You can choose the language of your preference in the lower horizontal menu. Este evento se enmarca en la Asamblea Anual Extraordinaria de Representantes de Arpel, congregando así a las máximas autoridades de nuestra asociación, además de altos ejecutivos de nuestras empresas socias. Alentamos muy especialmente a toda la audiencia a realizar preguntas, para lo cual les agradecemos a aquellos participantes por Zoom el favor de plantearlas por escrito a través del botón Q&A, también en el menú inferior en su pantalla. Rogamos a toda la audiencia presencial que desee conectarse al Zoom el favor de mantener sus micrófonos apagados durante todo el desarrollo del taller. Para participar, les agradecemos hacerlo únicamente utilizando los micrófonos inalámbricos en sala. El taller se va a grabar para luego compartirlo con el resto de nuestros socios. Daremos inicio al primer panel del día, para lo cual le voy a dar la palabra a Fernando San Martín, gerente de desarrollo de negocios para América del Sur y Central de Honeywell. Adelante, Fernando.
Muchas gracias, Irene. Muchas gracias a todos y todas, a los presentes en esta sala y a los asistentes virtuales. Esto para mí es un honor, moderar este panel. Vamos a ver inicialmente un video de Honeywell de tecnologías de sustentabilidad, dado que la mitad del presupuesto de investigación y desarrollo que nosotros gastábamos todos los años va en esta dirección, ¿no? Así que empezamos con este video, Daniela. Tenemos un tema técnico acá que resolvemos en un momento. Muy bien. Vamos a seguir entonces con la agenda. Me gustaría, en primer lugar, presentar a los panelistas. Si podemos movernos a la siguiente lámina, por favor. Muy bien, gracias. Bueno, vamos a tener a 4 panelistas para hablar de hidrógenos de colores acá, ¿no? Las reglas son básicamente las siguientes. Ellos van a tener 20 minutos para comentarnos de una determinada tecnología. Vamos a tener unos 5 minutos para preguntas y respuestas. Y luego, al final del panel, espero que tengamos tiempo también para seguir compartiendo e interactuando. Bien. Tenemos aquí a Jeff. Él es director de desarrollo de proyectos en Honeywell UOP para hidrógeno azul y captura de carbono. A Carol Sang, que es líder de desarrollo de negocios en la compañía Electric Hydrogen. Ellos desarrollan tecnología de electrolizadores PEM para hidrógeno verde, ¿no? Luego vamos a seguir con César. César trabaja en Ecopetrol y nos va a comentar de proyectos de hidrógeno blanco. Bien. Finalmente, Ezequiel, del ITEC, nos va a hablar de un proyecto de electrólisis en Argentina. Habiendo dicho eso, me gustaría partir la conversación con un diagrama que resume el balance de hidrógeno en todo el mundo, ¿no? Si puedes cambiar, por favor, la lámina. Disculpen el dibujo, la idea aquí es mostrar simplemente unos números que tienen que ver con lo siguiente. El 99% del hidrógeno que usamos en el mundo se produce a partir de fuentes fósiles sin abatir, y menos del 1% corresponde a hidrógeno azul o hidrógeno verde. Ahí están los números. Y luego, si miramos en el uso, ¿no?, del hidrógeno, gran parte de este hidrógeno tiene un uso bien tradicional en refinerías de petróleo y en la industria química. Luego hay una oportunidad de crecimiento importante para desplazar, ¿no es cierto?, ese hidrógeno gris por estos otros hidrógenos en el futuro, a través de proyectos de retrofit o bien en greenfields. Luego, me gustaría que nos detuviéramos un momento en ese 7% de otros usos. Ahí también hay una gran oportunidad para el hidrógeno. De esos 7 puntos, 6 corresponden al acero, ¿no?, al procesamiento del acero. Ciertamente ahí también se puede reemplazar el hidrógeno. Pero hay un otro punto que tiene que ver con una de las áreas de mayor crecimiento futuro para el hidrógeno como portador energético. ¿Haciendo qué? Produciendo energía eléctrica, o produciendo calor para uso en procesos industriales o bien para uso en edificios y en casas. Y también en transporte terrestre, transporte marítimo y en el futuro en transporte aéreo. De manera que hay grandes oportunidades para el hidrógeno bajo en carbono de crecimiento en el futuro. Y la idea de este panel, a través de nuestros panelistas, es comentar cómo desde la oferta nos hacemos cargo, ¿no es cierto?, de este desafío. No deseo decir nada más. A partir de ahora quisiera dejarlos con Jeff. Jeff, please go ahead.
Okay, can everyone hear me okay?
Yes.
Just sharing my screen. Okay, you see the screen okay? Okay, thanks,
Yes.
Carol. All right, it's my pleasure to be here and to be able to share a little bit more with you. You know, as Fernando mentioned, I work for Honeywell UOP. I'm based out of Chicago, Illinois, in the United States, and I support Honeywell UOP's carbon capture and blue hydrogen business. Today, I'm going to start by talking a little bit more about the hydrogen market. Fernando did a good introduction already, but I'll talk a little bit about our view, you know, both for demand and supply of hydrogen through the energy transition, and then talk very specifically about our blue hydrogen solutions through 2 different types of technology. The first being autothermal reforming, known as ATR, and the second being steam methane reforming, known as SMR, and the different solutions we can apply there. And then I'll wrap up with a little bit of time for questions. So we'll start by talking about the global hydrogen outlook. You know, as you can see on the left, there's kind of two threads to the story with hydrogen demand. You can see rapid growth from 2020 out through 2050. So about 90 million tons of hydrogen being used, in 2020. As Fernando mentioned, projected to be up to 140 million tons by the end of this decade, and up to 660 by 2050. So very rapid growth as hydrogen takes on an increased role in our global energy profile because of its potential as a zero emission fuel substitute across a large range of applications. The other thing to notice here is that you can see there's only one color bar in 2020, right? Almost all of the hydrogen being produced today is used for what we're calling existing industry use. And as Fernando mentioned, that really comes down to refining applications, fertilizer applications. That's the primary outlet for hydrogen today. But as we go forward, you can see the end uses of hydrogen become much more diverse. That's where we can see a future of actually using hydrogen to help support power generation, to provide building and industry heat as a fuel substitute, mobility. So this would in terms of fuel cell vehicles or heavy duty trucks, that could be powered by hydrogen for mobility, as well as new industry feedstock. So for example, to pivot steel production, pivot away from natural gas and use hydrogen in electric arc furnaces to produce lower carbon intensity steel. So very exciting space to be in, with hydrogen serving a lot of potential to help us through the energy transition. On the right-hand side, you can see that as this demand profile changes, the supply profile of hydrogen is also expected to change. So right now, again, today, almost all of the hydrogen being produced in the world, is gray hydrogen. Gray hydrogen refers to hydrogen that's produced from a fossil fuel feedstock, typically via like a steam methane reforming process with associated carbon dioxide emissions in that process. Blue hydrogen refers to that same production, but adding technology to significantly lower the carbon dioxide emissions associated with the process. So that's essentially adding carbon capture onto that production, either new production or existing production. Our view is that blue hydrogen is the technology that's ready today. It's technology that's been proven in the industry, and can be cost competitive with current incentives today, to produce blue hydrogen. Green hydrogen, which I know, Carol is going to talk about after me, refers to the electrolysis of water, typically using, some type of a renewable power source to split, the hydrogen and the oxygen and produce hydrogen from water. Green hydrogen, very exciting, holds a lot of promise to really solve a lot of our needs in the energy transition. We'll be very interested to see, what Carol is up to in this space. Our view has been that that's, a little bit secondary, to the blue hydrogen market, with really a lot of traction sort of happening post 2030, but certainly a lot of interest in that space right now and a lot of projects going through development phases. So that's really the story of hydrogen. And what I'm going to focus on is blue hydrogen, and what we have to enable blue hydrogen production today. These are the two technologies that I'll be talking about. On the left is steam methane reforming, and on the right, autothermal reforming. So the majority of hydrogen that's being produced today is through the steam methane reforming process. That's taking, natural gas or, methane, adding steam, operating over a catalyst to produce carbon monoxide and hydrogen, and then using a water gas shift reaction to further shift that CO with additional steam to produce additional CO2 and hydrogen. This process is endothermic, meaning it requires heat to work. So that's why you'll see there's an additional fuel source that's needed to provide the heat for this technology. The key thing to notice here is that out of the SMR unit is a syngas that's rich in hydrogen. That's what's being produced. But there's also a flue gas that's being produced in this process unit because of the need to provide an external fuel source and burn it. Okay. So you have carbon dioxide that's in this synthetic gas as well as in the flue gas. The autothermal reforming technology is different. You can see it's methane reacting with oxygen to produce the CO and the hydrogen, which again will go through a water gas shift. This technology produces heat within the reaction. So it's not as dependent on any type of external fuel gas. There is still a small amount, but most of the heat needed to facilitate the process is automatically generated, within the process. What's key about that then is that all of the carbon, from that feedstock is in this synthesis gas. Because there's not a large amount of external fuel gas, you're basically segregating all of the carbon in this syngas at a much higher concentration, meaning it's a really good opportunity to capture that carbon from that stream. So ATR is really being viewed as an attractive option for new blue hydrogen production because of its ability to really concentrate the carbon dioxide, in that synthetic gas stream and at a higher concentration. So let's talk a little bit about what we have in the space of autothermal reforming solutions. So as I mentioned before, the flow scheme is quite simple. You have natural gas going to your ATR unit with a water gas shift that's producing a hydrogen-rich syngas. Typical in the industry for any type of hydrogen production is it needs to go to a pressure swing adsorption unit that will convert that syngas, which could be in the 60 to 70% hydrogen range, into high purity hydrogen. So 99.9% or higher, which is typically what's required, in refining and fertilizer applications and what's expected, to really enable the hydrogen economy. The tail gas or the rejection gas from this pressure swing absorption unit is rich in carbon dioxide, so it could be between, again, 60 to 70% CO2 after it goes through the system, meaning it's a really good opportunity to capture that CO2. And when we think about capturing CO2, the higher concentration of the CO2, the more economical it is to capture. So what we're seeing in the marketplace is that these autothermal reforming units are really being looked at large world scale hydrogen production, largely because of the benefits that you get from scale and due to some of the high cost, to enable this process, for example, through this air separation unit. We have a number of solutions, that we can use to sort of tailor this to meet customer needs, delivering the hydrogen product at different grades with very high CO2 recovery and very high CO2 purity, making that CO2 available for both utilization as well as permanent geological storage. So if we look a little bit more closely at the flow scheme for this technology, we have our shifted syngas coming out of the autothermal reforming unit, goes through a cooler and a knockout drum to remove any entrained liquids, and then into our hydrogen PSA unit. And as I mentioned here, this stream is typically in the 60 to 70% hydrogen range, with the balance being carbon dioxide, unconverted methane, and some inerts like nitrogen and argon. The PSA unit is going to produce a high purity hydrogen product at high pressure, so in the range of 99.9% plus hydrogen purity. And it's going to reject the remaining components at low pressure. What we use in our system is a compressor to recompress it, a dryer to remove any liquids, and then send it to our CO2 fractionation system. So this is a fractionation technology, low temperature refrigeration technology, to fractionate and separate out CO2 as a liquid product with high purity. Coming off of the overhead of our CO2 fractionation system, we again have a hydrogen-rich gas, which can go to a PSA unit, which will reject any remaining CO2, which we can recycle to improve the overall CO2 recovery, and then further separate the hydrogen-rich gas for different uses. They could be used as a low carbon fuel within the process unit, could be recycled back to the autothermal reforming unit to improve the overall hydrogen recovery of the system. So hopefully that was clear enough. If you'll notice, the pink boxes are the technology blocks that we would supply. And you can see we've got significant industry experience deploying this technology. So we're the world leader in hydrogen PSA technology with over 1,100 units installed. We manufacture and supply molecular sieve adsorbents, which can be used for the drying of the gas. And our cryogenic fractionation experience is over 416 units, 3 of which are in direct CO2 separation service. And I'll be talking about that a little bit more in some subsequent slides. This technology is attractive for a number of reasons. I've listed them here. First, the high purity liquid CO2 product. A liquid CO2 product is a bit easier to handle, and when you need to bring it up to a higher pressure, you get some benefits from pumping rather than compressing a gas. High CO2 recovery to ensure we're capturing the CO2, not letting it get into the atmosphere. Commercially referenced with a high technology readiness level. We can enable very low carbon intensities for the hydrogen production, which is key in terms of certain incentives that are in place today. High reliability for the hydrogen production. Even if our cryogenic unit is down, this unit is still producing hydrogen, whereas other technology solutions that would be deployed upstream of the hydrogen PSA would mean that if there's any interruption in that equipment, the whole plant is no longer producing hydrogen. Finally, it's solvent-free with no special chemicals needing to be handled and with flexibility to produce multiple grades of hydrogen. This is just a quick view of the building blocks of what this looks like. This is our polybed pressure swing absorption unit. This is the molecular sieve dehydration unit, and this is a look at what the cryogenic system looks like. You can see the large tower associated with the fractionation and then the refrigeration section located nearby. All of this technology can be deployed in modular skids like this, which can really have some opportunity for reduced schedule at the site because all of this would be prefabricated and shipped directly to the site. In very large scale units, it's likelier that there might be multiple hydrogen PSAs associated with the CO2 fractionation and MolSiv dehy unit. In terms of commercial references, I mentioned there's 416 operating references, mostly in NGL and LPG recovery applications, but at very high flow rates, up to 1,575 million scuffs per day of gas being treated. This is over experience over the course of the last 50 years. On the right-hand side, you can see that there is specific experience related to CO2 separation for use of this technology, and at very large scale. So 8.4 million tons per year, almost 2 million tons per year, and 7 million tons per year. So these are very large in the scheme of carbon capture projects that are being considered today. I will point out this is the first one that is operating. These next to here are at various stages of engineering and construction. I'd like to share a case study, of what we really see being, kind of the trend in the industry. And that's for a project where Honeywell UOP technology was selected by ExxonMobil, Baytown, for what to date is the largest announced blue hydrogen project in the world. So ExxonMobil is they're in the feed right now for this project. They've selected Honeywell UOP technology. to become a world-scale blue hydrogen producer, both for their own internal use, to have hydrogen available to support the needs of their petrochemical plant, as well as to produce additional hydrogen that they can sell into the Houston market, both to existing users of hydrogen and to supply the hydrogen needed for the emerging hydrogen economy. So this is very large scale, producing almost 1 billion standard cubic feet per day of hydrogen, once it would be constructed and operating. You'll see the flow scheme is very similar to the simple representation I went through just before. I'll point out just a couple of unique differences. First, you'll notice this ATR fired fuel being extracted from the hydrogen PSA. This is key because it helps us lower the carbon intensity of the hydrogen production. And in the United States, the incentive framework for clean hydrogen production is based on the carbon intensity of that hydrogen. So any way to lower that improves the incentives available. Because of our expertise in pressure swing absorption, we're able to extract a carbon-free, low-pressure hydrogen stream from the PSA unit and use that as a fired fuel, reducing any carbon footprint associated with that gas. It also allows us to purge the inerts out of the system so that they don't build up while we're recycling. And it helps to reduce the duty on this compressor because we're extracting it upstream of this compressor unit. Second, I'll point out the CO2 product just so you see the scale. 7 million tons of carbon dioxide being produced annually as a liquid product, making that one of the largest carbon capture projects planned in the world. And then you'll see 2 sources of hydrogen production. The high purity, high pressure hydrogen production produced out of our first PSA, as well as a secondary hydrogen product at slightly lower pressure and lower purity through a membrane unit that can be used as an additional fuel source within the petrochemical plant at Baytown. So if you look at this here, you can see significant reduction in ExxonMobil emissions, significant production of hydrogen, and at very low carbon intensity. The only outlets in this system are the carbon-free fired fuel stream, the hydrogen product, and the CO2 product. So that means any carbon in the system, whether carbon dioxide or unconverted methane, will be recycled back to the ATR and will continue to recycle so that we're really capturing it all within our system. And the only associated emissions would be, upstream natural gas losses, or downstream, fuel requirements, meaning that it's a very low carbon intensity process. Now I'll pivot to talking about steam methane reforming. And the key with steam methane reforming, if you caught it before, is that there's a hydrogen-rich syngas, but there's also going to be a flue gas where there's going to be carbon dioxide being emitted. So typically about 60% of the CO2 can be captured in this pre-combustion loop, with the remaining 40% in the flue gas. And so that's important to note that while pre-combustion refers to the higher concentration streams and being a lower cost of capture to get at it, you're not addressing the full CO2 emission problem if you're not able to also treat this flue gas. So that's the real key consideration with an SMR. I'll cover this one rather quickly. We can employ the same scheme on an existing SMR where we take the tail gas from the PSA, run it through the CO2 fractionation system, produce an additional high purity hydrogen stream, and then recycle gas to the hydrogen burners after our CO2 fractionation system. So because of this additional high purity hydrogen that we're recovering through our system, we can use that incremental hydrogen recovery to reduce the costs associated with the CO2 capture. So you can see up to 20% additional hydrogen being recovered, High recovery from the PSA tail gas, 99% from the stream, but again, about 60% of the total CO2 emitted in the process. Multiple grades of CO2 can be produced, can be bolted onto an existing system, you know, and at a low dollar per ton cost of capture when you consider the benefit of the hydrogen credit. It is important to note that since we're adding this within a process unit and changing the gas to the burners in the SMR, you likely need a burner retrofit. Two other options. One would be a lower CapEx option where we use only CO2 PSA on the PSA tail gas. This will be slightly lower CO2 recovery and slightly lower CO2 purity, but does offer a lower CapEx and simpler installation if that would meet the needs of the CO2 product. And then finally, we can also use a solvent system upstream of the PSA. This is well referenced in the industry. Again, high CO2 recovery from the syngas, high purity CO2 being produced. Now, though, because we are installing this solvent solution upstream of the hydrogen PSA, we're changing the gas composition here, meaning you need to revamp this PSA as well as revamp the burners in the SMR. But this also offers a lot of references within the industry, number of customers very comfortable with this technology, looking at it as a way to implement carbon capture. The final option that I'm going to talk about is using a post-combustion carbon capture system, but this time directly on the flue gas. So here we allow the process to run as it's operating right now, recover the hydrogen, have your CO2 rich stream go directly to the burners, and do all of your carbon capture here on the flue gas. So this is a more complicated execution of carbon capture because now you have a low concentration and low pressure gas where you're doing the carbon capture. But we don't need to revamp any of the equipment, you know, that's currently in place. And this allows us to capture essentially all of the CO2. We're offering a total solution here because now we can capture about 95% of the total CO2 being emitted in the process. But because it's a lower concentration stream, it's at a higher cost on a dollar per ton basis. We have a unique solution, a unique solvent that we use in these type of applications that has some benefits related to the solvent characteristics to reduce the capex and opex of the system, you know, and it is a attractive opportunity for people looking to maximize carbon capture on existing SMR production, as well as other hard to abate areas in steel, cement, you know, power production as well. This is a overall view of what these technologies look like. The key is really to see what the carbon capture is. As I mentioned here, it's typically about 60% in the pre-combustion cases, but over 95% in the post-combustion case. But as you would expect in these pre-combustion cases, the cost on a dollar per ton basis is lower than what you would expect to see in a post-combustion case. But in all cases here, you know, there are positive economics that would facilitate developing carbon capture projects on hydrogen production today. So with that, hopefully on track with the timing, just like to wrap up.
Yes, please.
Decarbonized world shows a large growth in hydrogen demand with a pivot of blue to green hydrogen production over time. We have solutions for both ATR and SMR production, both in new units as well as existing units. And we've got the experience to be able to deploy this technology to meet specific customer goals related to carbon intensity, capture cost, capture rate, etc. So with that, I can wrap up, and Fernando, yeah, I can either take questions or hand it over to the next presenter.
Okay, thank you very much, Jeff. I think we are a little bit short of time, so I have one question for you that we would like to discuss. Regarding with blue hydrogen, what do you see more interest in retrofits in existing plant or new greenfields?
Yeah, so we're seeing a lot of interest. I would say right now the trend is really looking at new hydrogen production and specifically using the ATR process. Most customers who are looking to get into this are looking to expand their business opportunities as a world scale hydrogen producer, taking the benefits, the CapEx benefits of producing at large scale, and making use of the latest improvements in technology to really drive down the carbon intensity. As we noted before, using existing production, you're a bit limited in what you can do in terms of a carbon intensity perspective. And so that's what we're seeing drive forward in the market. And the ExxonMobil project is a perfect example of what we're seeing. And we've got a number of customers looking to produce similar type projects and really target that low carbon intensity hydrogen production.
Okay, thank you very much. If you have more questions, I think we can go back to the panel at the end of the session, okay? So having said that, Jeff, thank you very much. We will appreciate you stay to the end of the panel so we can discuss other aspects of this topic. So, Carol, are you ready?
Yes, let me just pull up my slides.
The session is yours.
Let me know if you guys can see my slides.
We've got it.
Great, thanks. Hi, everyone. My name's Carol Zhang, and I work at Electric Hydrogen on the commercial team. I've been at the company 2 years or so since the inception. Have worn a lot of hats in product marketing, but now I'm focused on customers and finding places to deploy our first projects. I'm gonna kind of lay out the roadmap of my presentation today. We're gonna probably spend the first section talking a little bit more about the hydrogen market, but with a green hydrogen lens. And then I'm gonna move into a deep dive of our product and what we offer. But before I jump into those two sections, it'll be helpful just to do a grounding and introduce us a little bit more formally. So we are a US-based company that is offering the next generation of ultra low cost electrolyzer systems to produce fossil-free electrolytic hydrogen at the industrial scale, but also most importantly, the industrial price point. And so what that really means is we are offering a product that is an integrated 100 megawatt electrolyzer plant. And if you see here on the bottom of this page, this is really a nice kind of conceptual, kind of de-featured version of our plant. Our plant is standardized, so every customer, when they come to us, they get a version of this plant and they get increments of this plant. And we offer, I think most importantly, larger scope than a lot of the other OEMs. We like to say we offer customers and developers and operators everything they need to take medium voltage electricity and roughly potable water and produce high pressure and high purity hydrogen. So 32 bar G and then 3 nines. And so in this rendering, you'll see at the very center, or maybe I start from the left side and move across. This is our power conversion and power transformation section, and this in the center is a power distribution center. And then along the center, you see a series of advanced PEM electrolysis stacks. And then the back half of the plant is the process modules that handle the water, cool the stacks, process the gas. And then in the back is an integrated dry cooling system. So that's our product in a nutshell. It's roughly 1.5 acres in footprint and produces around 50 tons per day. But I want to take a step back and really talk about the mission. Like, why are we operating and why are we commercializing this product? And it's really because critical sectors, like all the sectors that people in the room and virtually come from, need a lot of low-cost hydrogen to decarbonize, whether it's transportation, fertilizer, refining, steel, infrastructure, maritime, everything requires so much hydrogen to decarbonize, whether it's hydrogen, ammonia, methanol, et cetera. And today it contributes up to 25 to 30% of global emissions, and the opportunity to reduce further emissions as new use cases for hydrogen open up is enormous, as Jeff mentioned. And so when we think about the hurdles for green hydrogen adoption, it's really an economic issue, right? Green hydrogen today is far too expensive, and it's not competitive with gray hydrogen produced from SMRs today. So when we talk about cost competitiveness at our company, we really don't talk about us against other green hydrogen OEMs and what their systems and machines can produce, but rather the price to beat for us is gray hydrogen. And so to really ground us in what that means is that it's roughly $1.50 to $2.50 per kilogram is the price to beat for green hydrogen. So it won't be until that point where we are able to produce a levelized cost of hydrogen of about $50 to $2.50 that the economic argument for green hydrogen makes sense. And as we all know, the industrial sector doesn't make decisions based off of green premiums. It has to pan out economically. And if you look at where we're at today in terms of how much it costs to produce green hydrogen, a kilogram of green hydrogen, it sits anywhere from $4 to $6 to $7, depending on where you are. And different areas in the world are kind of blessed with different resources that really drives that. Something that we have published as a company is a public use calculator for customers and partners and stakeholders in the industry to really understand what are the drivers of green hydrogen production. And I'll quickly flip to what that looks like. So if you go to our website at eh2.com/toolkit, it has a suite of electrolysis modeling tools, essentially. And we call our model LCOH, quite simply, because that's what it models. And it has a set of inputs that have kind of key considerations and inputs into what drives the dollar per kilogram number of green hydrogen. So you'll see CapEx here, cost of electricity, capacity factor, or how much you run it, and then it spits out a levelized cost of hydrogen. So I'd encourage you, if you guys are curious, to play around with this tool after today's session. But that's essentially what's driving all the numbers to the right here. So we see today gray, natural gas-based hydrogen stands at roughly like $2 to $3 per kilogram today. Green hydrogen, on the other hand, is nowhere near in the ballpark. And so that's where we are. And so we as a company were born to address this problem. So the formula for fossil parity green hydrogen is really, to have cheap hydrogen, you need cheap power. And it takes anywhere from like 50 to 55 kilowatt hours per kilogram to produce a kilogram of hydrogen. And so you think about it, it's a huge cost driver. So you need cheap power. And it turns out in most parts of the world that cheap green power is intermittent or has lower capacity factor. And so what that means is the only lever that you can pull in many geographies is necessitating really low cost electrolyzer systems. And so what does low cost mean? It's not what we have today. And the IEA publishes a global hydrogen view of what the total installed costs of green hydrogen plants are for alkaline and PEM. And it turns out over the last 3 years, we're going in the wrong direction. So these estimates have only gone up. In the last year, their estimates for alkaline and PEM have gone up 15 to 20%, as you can see here. So in order to solve the cost problem, as we discussed, we need to be able to offer a low cost solution for electrolysis. And that's when we come in. And so what we're offering to the market for the same scope of project deployment is a transformational product offering that slashes the cost of electrolyzer plants by nearly 30 or 40%. And let's say, this band at the very center sits roughly around $750 per kilowatt. And if we model that through, we see that we're not quite at parity, but we're a lot closer to what it would take to beat out green hydrogen economically, at least. And so how exactly are we able to do this? That's probably the big question. You know, everyone else has been building these plants at $2,000 per kilowatt. How are you able to do it at $750 to $800 per kilowatt? And the solution is this. You know, we're standardizing on a 100 megawatt increment or unit for electrolysis plant deployment. And so this is a conceptual rendering of all the different equipment areas that we include in our product. So we have the gas separation, water treatment, electrolyzer, and the plant controls and power conversion. But another really big way that we're reducing costs of electrolyzer plants is through our product deployment model. So not only are we drawing our scope a lot bigger in that we're offering all of these equipment areas, our product is entirely prefabricated off-site on a set of skids. And they arrive to the customer site on a set of 75 or so skids, and then are field assembled over the course of 2 or 3 months, and then commissioned over the next 2. So if you think about from first shipment to commissioned plant, it's 6 months. So that's drastically reducing the in-field time of deployment and construction when most plants out there are kind of custom stick build. So in terms of how this fits into the green hydrogen OEM market, the kind of key differentiators for us are that we offer a complete solution. So we are a turnkey solution in that we don't just give you the stacks or the rectifiers or the gas separation. We give you everything that you need to take electricity and water and turn it into high pressure and purity hydrogen. Secondly is that we offer really powerful stacks, and that's a key part of our cost reduction story. We basically have developed our own kind of a form of advanced PEM electrolysis that increases the capital efficiency of the electrolyzer stack so that we get more hydrogen output for the same stack assembly. And we in turn pass those costs, cost reductions onto the customer in terms of the price of the plant that we sell. And lastly is that we offer a very efficient plant. So our electrolyzer is co-optimized with our 100 megawatt plant design, but also most importantly, our rectifier system. And so what really you'll see in deploying our plants is that you'll see reduced project engineering costs because the 100 megawatt plant unit is already pre-engineered and pre-designed, reduced construction costs because the plant is pre-assembled, a lower CapEx because of our innovations at the electrolyzer stack level, but also in our innovations in procurement and managing our supply chain. You'll also see lower OpEx. We operate on dry cooling and have a lower electrical intensity. And these are some more numbers that add more context to the impacts today on levelized cost of hydrogen. So if you look at some of the assumptions we had before, conventional PEM will get you at best case at $3.50, $4. Alkaline's a little bit less. It's been around longer. It's more widely deployed. And where we stand today at our current price points, customers are seeing prices in the range of $250 to $350. And so in terms of our company and our journey, we are roughly 300 people today. We need to update this number. We have a prototype plant sitting not too far away from me in San Carlos, California. We are commissioning our first pilot plant, which is roughly 10 megawatts later this year. And then we are shipping our first 100 megawatt product next summer to a customer in Texas. We're based out of the US. We're bi-coastal. A lot of our plant engineering and power systems engineering sits on the West Coast. And then on the East Coast, we have a lot of our electrochemistry and manufacturing for our electrolyzer stacks. This is some recent traction that we've had that we've announced. So our first 100 megawatt plant, as I mentioned, is going to a customer called New Fortress Energy, going to Beaumont, Texas. It's right next to an OCI plant and will supply the green hydrogen for them to produce green ammonia. We also announced a nearly $400 million Series C round a few months ago, so we're well capitalized all the way through scale up and deployment. And that's it. I'm happy to take any questions or wait until the end.
Thank you, Carol. A very interesting approach of a modular system, right? I think we have at least one question. What about the growing demand? Looks like green hydrogen is taking momentum. So how are you getting prepared for that that demand?
Yeah, so right now our focus is on serving demand in the US. We are commercializing our first product. We certified and operating in the US, and we announced our first gigafactory to be based out of Devens, Massachusetts, which will have a nameplate of production at 1.2 gigawatts, which is not nearly enough to serve even a percentage of the global demand of hydrogen that we're talking about. We are probably going to site a second factory in the US in the near term, but then now are actively investigating, the next geography, whether it's Latin America, the EU, or Australia, and we're talking to customers like those in the room to understand the opportunity in each.
Good. And I don't know if there is a question for Carol in this moment, or should we wait for the end of the panel? Pardon. No? Okay, Carol. Thank you very much for your presentation, very clear. We will move to the next speaker. Muchas gracias. Certainly we will appreciate if you can stay at the end of the panel to final questions. Gracias. Bueno, ahora seguimos con Ecopetrol. César, por favor, la audiencia es tuya. César nos va a hablar de un proyecto de tecnologías de hidrógeno blanco.
Thank you. Good afternoon, everyone. Thank you for the opportunity for being here on this representation. Thanks to the previous panelists.
César, César, discúlpame que te interrumpa. Puedes presentar en español sin problemas, ¿no? La mayoría de la audiencia habla español. Muchas gracias.
Okay.
Perdón por la interrupción.
Okay, thank you. Just no problem with that. I can go as well on English if this is okay, just with the other previous speakers too. And this coming as well on the while we are working today in the current strategy on hydrogen. That's come related to how today we are putting together different scenarios on a profitable way. Include the hydrogen volumes on the goal of 2040. These come with 3 types of hydrogens in the roadmap: green hydrogen, blue hydrogen, and white hydrogen. We have on this scenario, on this time, we are going to have a talk about white hydrogen. We have been seeing cases about the blue and the green. So in Ecopetrol, we are working about the white. And what is coming about the white is something that new technologies and how we can connect the different scenarios on a competitive and profitable manner put together on the different horizons. In this case, on this scenario, what do we have here today is to see how the knowledge we already have on the oil and gas business can contribute to this change on the energy transition scenario. So it's something that we have been already started since 3 years ago. We have been started on 2022, taking samples of white hydrogen. You can see about the strategy and how the portfolio we have been taking into account these considerations. It's something that we have been already discussed and talked previously. You have been following Ecopetrol strategy information. But this year as well, we have been already doing analysis and continue understanding and include new technology options related to white hydrogen. In that sense, what we are doing on this natural hydrogen scenario is put low emissions hydrogen in the understanding of the subsurface. And that is the way that today, on a vertical way, we are putting the information, the technology, the acquisition that we have been getting from the mature field assets, from the understanding of the geological understanding do we have from the oil and gas industry, because, do we have the reservoir information, we have a deep information data acquisition, we have as well processes underground and processes on surface that we should connect. So understand the different natural resources is something that we are putting now in place, understanding from the geoscience perspective On this geoscience perspective, you have in the reservoir, we have temperature, we have aquifers, we have CO2 storage, the one that we use for the CCS or the blue hydrogen is something that comes as well related to what do we have in our understanding. But we have aquifers downhole, and this knowledge that we have it in downhole is something that we should apply as well to see how we can do a synergy with the information we already acquire. So in that manner, the subsurface resources overlap on different alternatives or the basin that we already have it studied to explore and to bring energy from the hydrocarbons. But now we are putting new energies with low emissions coming into the hydrogen ecosystem with the natural hydrogen, with the knowledge that we have. And this comes from the geological understanding. And that's why this comes as well from the what people and scientists and today different exploration, new frontiers, options in technology and innovation is bringing the geological hydrogen storage and capture and options as well hydrogen into the system. So in that sense, it's something that we start to be working on a special estimate of the natural hydrogen into the basins, looking into the asset we have it in Ecopetrol business group. In the different assets we have, these alternatives, and looking forward to have the feasibility of natural hydrogen on the basin that can correlate with the resources do we have it underground. This comes with the probabilistic scenarios as resources. This comes as well with a special lead and prospects. And this comes as well what is happening today in the geoscientist options with the geological hydrogen coming from natural geological or gold hydrogen that in some cases not name it, but this come all related to low emissions hydrogen. Hidrógeno blanco, as we say in Spanish, but this is now coming like a low emissions hydrogen that in 2011 was a discovery, a natural hydrogen discovery come in Mali, in Africa, with a bit challenges, a bit opportunity to increase and to provide energy, but as well to provide ammonia resources that can provide special products in Mali. And this comes as well with the opportunity that in Colombia do we have with the Colombia's hydrogen roadmap. As you know, here the government and the industry has a special roadmap that include either lines and items to be working on natural hydrogens like line 17 and line 18. We have been taking this challenge, we have been taking this opportunity to how we can integrate with technology, with the already innovation and alternative knowledge that we have it already for the basin, to do a cross-check and bringing these options in the new scenarios of the renewables, or the new scenarios of the carbonized energy portfolio that can come as well from the geological understanding. And this is why we have it as well accepted and see how the world is moving forward on that. And we can see here how Australia today is doing some basin already assignments and blocks or exploration that come with hydrocarbon synergy or resources on that one. Colombia wants to do as well. A lot of countries are working now on this one. So there are different projects that has, as we mentioned before, the synergy of hydrocarbon, the synergy or another resources, and the hydrogen resources that have been already identified in the wells, have been already identified on the basin, like a new opportunity for the companies to provide value, to become scenarios with renewables like hydrogen can come as well on that one. And this come as well with economical benefits that today special resources and reserves management systems that come related to special stock bank or stock values that we have it can be applied for the natural hydrogen. So the perspective or the prospective of the resources of natural hydrogen has been already starting to be quantified, giving economics to the hydrogen tons that can be given by the geological things. So that is something that now the invitation is for all these hydrogen ecosystem to put as well not only the green and the blue one, but as well the white one, or the natural hydrogen, on the perspective and the value of the different companies, because the market is giving value now on that one. The resource evaluation, the company with exploration and production on this will be having some values as well, and that is something that has been already recognized around the world and is working on that. And when I mention that is something that is recognized around the world, that is something that is not happening only in Colombia. We are doing studies around the world to understanding where can be these natural hydrogen resources come. United States is starting an aggressive campaign to acquire information, to start to put workflows related to the natural hydrogen perspective, even from Nebraska, from Kansas, and from some areas in North America. But as well, we have in Europe, Spain, France, and other areas of Europe, Russia, that have become with some understanding. China is working on these natural geological options, and as well the discovery of Mali and perspective as well in Namibia and other countries around South Africa can come as well in Africa, but as well Australia is by today the primary area, and actually in 2 weeks is going to be a natural hydrogen world technical conference where all the evaluation and the results that have been taken on this consideration and explorations are coming with more values related to this type of hydrogen. This type of hydrogen is provided by Natura, and this type of hydrogen will be found at different depths. Can be surface, can be a medium depth or deepest depth. But as well, this type of hydrogen can be found like free gas, like gas in inclusion, or dissolved gas. So we can find carriers, natural carriers, bringing the hydrogen from Natura, and it's something that we have been studying, not only the geological, but as well the geochemical, and as well the processes that can be created with this type of hydrogen from the surface. And how we are going to explode or do the production of this type of different basin and geological constraints is something that we are putting in this one. Before, light oil was not used in some basins and some part of the humanity history. Before, gas as well was not taken seriously as part of the ecosystem on energy. Before, another type of resources have been not taken in consideration. The resources that we have not identified no means that has no value. Different ages in the history have been giving us the reason that we should add value to all the resources we have in Natura. Today is the time for the natural hydrogen to bring this knowledge, to bring this identification. And that is something that now we are changing the glasses. We are just changing a new filter on what we are seeing on the exploration and geoscientific to put together the knowledge we have already from the subsurface and see how we can integrate the technology and the different options on this type of resources from ground to surface and become part of the hydrogen ecosystem that the different countries has. Latin America is already working a lot as well on that one. Brazil is doing some exploration. We have some activities in Uruguay. Argentina is trying to do some unconventional correlation with hydrogen. We have in Bolivia, we have in Colombia, and as well, we are trying to put what Natura is giving on the different system. From a craton system where the hydrogen can be recreated with iron, as happening in some of the energy storage options or some options we use in surface. Natura is using iron plus temperature plus special conditions on the geological perspective that can generate a free optional hydrogen. Water with solubility above 50 degrees Celsius start to have optional solubility. So water can work like an optional carrier to put the hydrogen into the system, and the fall systems bring the hydrogen from bottom to surface. That as well can come with the opportunity to put the well sites, the technology that we already have been doing for exploration, productions, and to transport, and to integrate all the chain value of the hydrocarbon system now into the hydrogen geological system. And that's why it's opportunity of technology and innovation with knowledge that we already have been acquired from the different basins to understand how we can put this one together. But this requires as well from special laws from a special government application, and that's something that Australia, France, special countries in Europe has a special law related to this one. And as well here in Latin America, in the case of Colombia, soon a law regulation will become out to have these exploration blocks, same as Australia, and production related to this one. So it's going to be a good play to be for doing investment on this type of scenarios. But as well, a growing ecosystem with technology is putting the previous exploration companies that used to have oil and gas operation business to move forward, as is happening on geothermal, into the hydrogen opportunities. Hydrogen opportunities that had special studies, either that had a special combination in the exploration with helium. So hydrogen plus helium plus special gases that we have in boron is something that we have been now putting into the synergy of the knowledge and technology and innovation we have from the exploration and service provider companies. We already have been working here in Colombia with some of the companies that have been providing some of the service for the chain value to understanding the underground, but as well to provide special technologies to make this happen, to provide option in surface. Colombia, but as well France, is doing this type of analysis, try to recreating and put in the scenarios different areas of information, data, technology that can provide these options of the geological constraints. That as well happening in France, in Spain, where hydrogen have been identified at the Pyrenees, as you have been seeing on the news and some of the options. And hydrogen is not coming alone. Hydrogen is coming with CO2, with methane, with H2S, with helium, and another type of gases. So looking into what is producing and how we are going to provide it to the industry is part as well what we are doing in surface, in some of the processes. So how we are going to put the different elements in surface, but as well in underground, is a challenge do we have it. The same happening in Spain, where now hydrogen and helium have become with the special areas in Aragon, where they have a special geological discovery, where they have it, this option, but as well in some areas near to France, where they have it. So the move of hydrogen started on Mali on 2011, where some wells, today around 21, are producing around 98% pure hydrogen from underground. We are understanding the technology. We are understanding the behavior of the different data and information that we have been already acquired on the ground to put and understand these 98% on hydrogen in surface that as well can come with nitrogen or methane or another gases to identify how we can produce that one. These are pictures of the first well that have been in white hydrogen delivery, this type of gas, under the condition of the different geological option that we are trying to understand around the world, around the geological constraint, to have these main sources and to open the valve to low emissions hydrogen that come as well with opportunities in economics, as we see in Australia. So Australia is continuing doing an aggressive campaign to put this exploration with natural hydrogen at the different areas of Australia, doing the blocks, as we mentioned before, but as well doing synergy of the technology and the knowledge we have in underground. So there are different perspectives, but as well there are options that include natural hydrogen on the perspective we have it for our renewable portfolio is something that will become. We have been founded some expressions of these options in Brazil, in Colombia, that we can come together as well in United States, where you can see how hydrogen is coming out from the ground. It's coming out from the measurements we are taking on surface with a special camera, with a special measurement. So it's not something that is not happening. It's happening, and it's producing by the natural option of the natural hydrogen that as well is coming with the different explorations in another areas in the United States that have been taking opportunity of the well size and the conditions with exploration and found it with another type of gases as well. There are some exploration and some investments as well coming around this type of natural hydrogen, and for sure you have been seeing this type of news on the social medias, on the social networks, but it's not only this type of investors is happening. Today, governments, institutions, and companies like ours are working on that one. So this comes with this scenario we mentioned before on the ecosystem, and is what we are doing in Colombia. we have been identified a special area and basins where we can find this type of scenario that is happening around the world that can provide the special geological scenarios and geological options that can put into the different basins. What do we have it? How we can put the value to that options, and it's something from the Llanos Basin to the Pacific system is something that we are putting and working. We already have been recreating workflows. We are working on identify special elements on the knowledge we already have it, where we have been applied technology from the understanding from the underground, from the processes, from the accumulation, and as well for the production. So in this sense, we are doing integration from different previous methods of technology, from the regional geology, for the special gas chromatography, as the gas chromatography you use in surface, but we use it in underground, geophysical knowledge, remote sensor, with satellite information, to all this one integrate the hydrogen system that is not only to be in a special base, it's going to be on a big scale that can come with the production we have it. Coming from underground is something that we put in technology, understanding from the geophysics, from technology that as well to different scale that come with mega scale to nano scale is something that we are working as well to do this type of integration. But the good news is we already identify as well. We have been already flows of hydrogen in surface. This we can see on the meter about 1,000 ppms are coming out in some of the areas we have been identified in underground, in house. So that is something coming from underground and surface, and nature is producing this type of hydrogen resources that as well another study have been doing by the academia, by the university, identify hydrogen, methane, CO2, oxygen, and H2 related to some of these basins. So we are working on that sense. We are publishing more and more about natural hydrogen, and we hope this give you value on the hydrogen route that we are working together with the different international community, and we will see how we can put together these volumes of hydrogen at the different geological environments and options that can be replicated in the Latin America scenarios to find a natural source and resources of the environment to put together this industrial application. One thing and one important thing is the industrial health. It's very important to put technology on this one, to co-create, to bring the alternatives of this geoscientific knowledge with the technology you already have in surface, and we can create scenarios or the carriers, or how we handle, or how we are going to produce, or how we are taking opportunities from the natural opportunities to this hydrogen ecosystem on the coexistence of the energy transition alternatives. With that, I would like to say thank you to the different institutions that have been already helping us to be working on the natural hydrogen, from the Low Emission Vice Presidency, Upstream, Technology and Innovation, Research Institute, HOCOL and Ecopetrol, and different service provider companies that have been working with us. I will be open for questions. Thank you.
Excelente, muchas gracias, César. Personalmente no sabía que teníamos un recurso como el hidrógeno bajo la tierra, ¿no? Es un aprendizaje para mí hoy día, es una gran noticia. Y por otro lado, quisiera hacerte dos preguntas, y vamos a tener el panel acá también, ¿no? La primera de ellas es, ¿en qué horizonte de tiempo tú ves viable contar con este recurso a un nivel de producción industrial? Estimativamente hablando, ¿no? Dada la exploración que hay que hacer y todo eso.
Ok. Recordemos que hoy día en Malí ya está en producción industrial. Malí ya está produciendo energía.
Sí, yo me refiero a la región acá en Latinoamérica, ¿no?
La región en Latinoamérica, bueno, pues va a depender del tamaño de los descubrimientos que traigamos. Pues vemos que Argentina, Uruguay, Brasil, Colombia están trabajando agresivamente en estos escenarios, y lo bueno es los volúmenes. Aquí nos toca es, además de identificarlo, es cómo lo ponemos en producción, la pregunta que tú estás haciendo. Entonces, traer esos pozos, traer las celdas fotovoltaicas para conversión de energía de cabezal de pozo y ponerlo, pues eso ya está en el mercado. De manera que nos queda es identificar geológicamente el yacimiento, saber que va a ser comercial su producción y lo vamos a poder en casa. Entonces, como un pozo exploratorio, eso va entre 3, 5 años yo creo, y pues de igual forma el avance y el trabajo mancomunado o sinérgico que se está dando hoy día entre la geociencia mundial por desarrollar este tipo de hidrógeno es súper acelerado. De manera que yo pienso que de 3 a 5 años estaremos incorporando este tipo de recurso en América Latina.
Muchas gracias. Tengo una segunda pregunta, aprovechando que estás ahí, respecto de cómo ustedes en Ecopetrol ven la colaboración con compañías de tecnología en este mundo del hidrógeno bajo en carbono. Si puedes comentarnos algo al respecto, obviamente están haciendo colaboración y qué nos puedes decir al respecto.
Claro que sí, Fernando, y pues yo creo que ha sido parte de la estrategia que ya ha tomado la compañía en los años desde que salió la hoja de ruta estratégica del hidrógeno. Ha sido parte de los pilares estar trabajando con compañías como algunas de las compañías que están hoy día en la audiencia y que están hoy día virtualmente. Ya estamos trabajando con algunas de las compañías en hidrógeno verde y en hidrógeno azul, así como en las opciones de movilidad, en las opciones de mirar otras alternativas para desarrollar casos de negocios. Entonces, esa es la apertura total. En cuanto al hidrógeno blanco, ya han habido inversionistas que han venido no tan solamente a Ecopetrol, sino al Ministerio de Minas y Energía de Colombia, buscando crear ese tipo de sinergias y oportunidades. La compañía está abierta en ese trabajo para continuar con la perforación de esos pozos en hidrógeno que queremos y de igual forma traer la tecnología en sinergia para poder desarrollar esa producción y oportunidades regionales y más aún con la estrategia que se está dando ya al país de comunidades energéticas locales y su desarrollo. Y vimos que geográficamente pues es algo que se puede dar, donde hay diferentes sectores industriales, desde el agrícola hasta el industrial, por la diversidad del país. Entonces, hay apertura en ese sentido, es algo que ya está dentro de la estrategia y muy seguramente pues la apertura con ustedes va a estar ahí.
Muchas gracias. Bueno, vamos a seguir con el último panelista. Ezequiel, te tocó al final. Estamos muy ansiosos también de escucharte, de lo que nos puedes decir de los proyectos que están desarrollando como ITEC en Argentina.
¿Me escuchan?
Sí, perfectamente.
Perfecto, comparto pantalla para ver. ¿Me confirman si se ve bien la presentación? Perfecto, bueno. I will speak in Spanish in case someone wants to switch to the other channel, to English channel, but I'm going to speak in Spanish. Entonces, primero, muchísimas gracias por la invitación. Nos parecía muy pertinente desde ITEC poder participar en este taller, sobre todo si estamos hablando de tecnologías aplicadas al hidrógeno, poder contarles en el proyecto en el que particularmente yo estoy trabajando en este momento, que es el desarrollo de un primer electrolizador de alta potencia en Argentina. Rápidamente, permítanles contarles la compañía en la que estamos trabajando. ITEC es una compañía que es un 51% de YPF. YPF es la empresa de energía más grande del país y tiene una alianza estratégica con lo que se conoce como CONICET, que es nuestro centro que nuclea todo lo que sería investigación y desarrollo a nivel nacional. Esta simbiosis que se generó entre ambas, entre la compañía y esta institución, ha generado una compañía que es líder en lo que son soluciones aplicadas ya a la industria energética. Nosotros hemos cumplido el año pasado 10 años, la compañía, y la verdad que los invito a lo que puedan conocerlas y puedan visitar alguna vez, pero realmente no solo en términos de edilicio, el edificio es muy bonito, sino que también contamos con equipamiento de última generación que nos convierte en uno de los centros de investigación más grandes de la región, con más de 40 laboratorios, más de 10 plantas pilotos, enfocadas 100% en soluciones a la industria energética. Una de nuestras primeras iniciativas que tomamos con hidrógeno, porque dentro del abanico de soluciones en las que se trabaja dentro de ITEC, seguro el oil and gas es una de ellas, pero en todo lo que son soluciones relacionadas con transición energética y energías renovables y de transición, una de las primeras iniciativas que se toman y que es importante que mencionemos es el consorcio H2A. El consorcio H2A nace en el año 2020 con el objetivo de decir, bueno, ¿quiénes son los que están interesados? ¿Quiénes son los actores que están con un interés en el desarrollo de la economía del hidrógeno en Argentina? Hoy en día forman parte más de 60 empresas, son miembros del consorcio, que están distribuidas en 8 células de trabajo, que se logró realmente un trabajo colaborativo muy fructífero que ha llevado a diferentes productos o diferentes outputs que les voy a comentar en breve, pero bajo el liderazgo de ITEC también se ha logrado este último tiempo expandir este efecto que está generando el consorcio con diferentes alianzas también a nivel internacional y diferentes partnerships con otros organismos que sirven como asesores o que sirven como consultores en términos de intercambio de información. Estas son las empresas que hoy en día forman parte del consorcio. Pueden ver que hay empresas del rubro del oil and gas, upstream, downstream, hay puertos, empresas relacionadas con energía eléctrica, hay proveedores de tecnología, varias automotrices, tenemos empresas vinculadas con el mundo de los fertilizantes. La verdad que el espectro que contamos de empresas que forman parte del consorcio es muy amplio, lo cual enriquece mucho el trabajo y la interacción entre las diferentes empresas y lo cual genera justamente que se puedan genera que se puedan crear espacios en los cuales el intercambio, el networking y los futuros proyectos se empiecen a discutir y, ¿por qué no, viabilizar? El consorcio viene trabajando en 3 pilares, o se ha desarrollado en 3 pilares principalmente. El primero tiene que ver con el desarrollo de conocimiento. ¿A qué nos referimos? Hemos encontrado muchas veces valores de costo de hidrógeno o diferentes estadísticas o diferentes informes o reportes que nos cuentan con respecto a la oportunidad del hidrógeno en diferentes partes, pero no contábamos con valores de la realidad actual con la que contaba el país. Entonces, un primer seteo, un primer trabajo fue, bueno, veamos cuáles son los números específicos para Argentina, y en función de esos resultados se ha podido justamente ver cuáles son los puntos en donde tenemos oportunidades y dónde vamos a enfrentar los principales desafíos. Esto ha generado, por supuesto, una gran interacción entre los diferentes miembros del consorcio, y también esto ha llevado a que se empiecen a generar diferentes estudios de prefactibilidad de potenciales proyectos. Esto, por supuesto, también fomenta o fogonea justamente el intercambio entre el interesado en consumir hidrógeno, entre el tecnólogo, y también ha llevado con el tiempo, una vez que fue madurando el consorcio y fueron madurando un poco estas interacciones, ha llevado también a una interacción a nivel con las autoridades. Hace no mucho en Argentina se ha presentado la hoja de ruta del hidrógeno, como viene sucediendo en otros países de la región, y ha sido consultado el consorcio como un poco la voz a nivel industrial o la voz que aúna a todas estas empresas involucradas o que están interesadas en el desarrollo de la economía del hidrógeno, que pudieron justamente dar su opinión, dar comentarios o alimentar esta hoja de ruta que se está planeando, que ya se publicó a nivel nacional. Esos fueron como los 3 pilares en los que se viene trabajando y se está trabajando en el consorcio. Comentarles que en Argentina hoy en día ya se produce hidrógeno, y esta fotografía es muy similar a la que mostraron al principio, solo que en escala local. Hoy en día ya se produce hidrógeno en Argentina. Si bien el porcentaje a nivel mundial es bajo, de lo que pesa en comparación a la producción mundial, se repite la historia de que el hidrógeno que se está produciendo hoy en día es un hidrógeno gris proveniente de fuentes fósiles. Pero lo que sí me gustaría destacar son 2 cosas. La primera es el uso de este hidrógeno. Hoy en día ya está yendo a las 4 industrias principales demandantes de hidrógeno a nivel mundial, que es la industria de los fertilizantes, la industria del acero, la industria del metanol, la industria de la refinería. Quiere decir que ya contamos con una experiencia o ya contamos con compañías en el manejo de hidrógeno para estas aplicaciones que son las que se proyectan y se pueden ver que son las más demandadas a nivel mundial. Otra cosa que quisiera destacar, pueden ver en la línea de producción un porcentaje bajo de lo que es electrólisis. Nosotros tenemos el caso a nivel país de una compañía que ya desde el año 2008, bastante pioneros a nivel mundial, han instalado un sistema de electrólisis con el cual desde esa fecha hasta el día de hoy han realizado diferentes pruebas y hoy en día es una empresa bastante pionera en términos de producción de hidrógeno por medio de electrólisis. Esto también es un panorama que es extraído, como les decía, de la estrategia que acaba de publicar Argentina. Más allá del número en específico, un poco lo que plantea es que a nivel regional, las diferentes hojas de ruta que están planteando los diferentes países a diferentes momentos, 2025, 2030, 2050, no importa, es un gran crecimiento en la demanda de electrólisis que se va a requerir. Particularmente en Argentina, lo que estaban planteando es un gran crecimiento en la producción de hidrógeno, tanto en primer lugar para consumo interno, pero sobre todo también para exportación, que va a requerir un incremento, por un lado, de la potencia de electrólisis a instalar, y por otro lado va a requerir, en consecuencia, un incremento de la energía renovable asociada a esa electrólisis. A lo largo de las diferentes presentaciones que fueron viendo en el día de hoy, supongo que también por lo que vi de la agenda lo seguirán viendo. En términos generales, el mundo, si nosotros seguimos los escenarios de transición energética, los escenarios de descarbonización, vamos a requerir una cierta cantidad de hidrógeno. Pero tenemos que entender si vamos a poder abastecer de esa cierta cantidad de hidrógeno al mundo. Ya se ha encontrado que va a ser muy difícil cumplir con esa expectativa, y uno de los cuellos de botella con los que nos estamos topando es la disponibilidad, la accesibilidad a electrolizadores que permitan justamente la producción de este hidrógeno. Nosotros esto le podemos sumar una capa más al análisis, y es que ¿dónde se encuentran los principales fabricantes de equipos, hablando de forma genérica, que pueden producir hidrógeno? Se encuentran en el hemisferio norte. Esto, más allá de pensarlo con un término de localización de las factorías y demás, genera un plus a la disponibilidad del equipamiento. Genera un escalón más que tenemos que llevar a cabo para poder conseguir la tecnología puesta en el lugar donde nosotros la necesitamos. Hay dos comentarios que quisiera hacer al respecto, que son dos como noticias que se puede recabar de la información. Por un lado, en Brasil hay una compañía llamada Hytron, que es un spin-off de una universidad, fue adquirida por el grupo NEA, y en Chile la empresa Corfo hizo un request for information, justamente teniendo en cuenta compañías que tengan capacidad o que tengan interés en fabricar electrolizadores. Por todo este contexto que yo les estoy contando, es que desde ITEC, YPF Tecnología, se ha tomado como proyecto estratégico justamente el desarrollo, la construcción y optimización de un electrolizador alcalino de alta potencia, superando el megavatio de potencia, para la producción de hidrógeno verde, que en principio este primer prototipo que se está pensando y se está trabajando va a ser empleado en una industria vinculada en la industria del acero, para el reemplazo de gas natural prácticamente. Antes de avanzar un poco en el proyecto, quiero detenerme en dos palabras en particular que he empleado, o dos términos. Primero es que estamos hablando de un electrolizador alcalino. ¿Por qué estamos hablando de un electrolizador alcalino? Básicamente, los motivos que nos llevan a iniciar este proyecto, que ya lleva más o menos un año de vida, es que la tecnología alcalina, en primer lugar, hoy en día es la que tiene mayor porción en el mercado, es un poco la que ha recorrido más camino, y eso genera que pueda obtenerse muchas veces costos más competitivos, pero al mismo tiempo también nos muestra que es la que tenemos más información en términos de publicaciones científicas, como en términos también a partir de los mismos tecnólogos. Por otro lado, también, teniendo en cuenta las diferentes tecnologías de electrólisis que hay, es la que nos permitiría tener un desarrollo con mayor componentes de industria local versus a otras tecnologías. Entonces, es por ese motivo que se elige la tecnología de electrólisis como una primera tecnología para iniciar este proyecto. Otro comentario que quisiera hacer es respecto a la escala de tratar de superar el megavatio de potencia. Si bien obviamente vemos las hojas de rutas que yo les acabo de mostrar anteriormente, o los valores con los que se vienen conversando en las presentaciones anteriores, un megavatio puede parecer que es una cantidad pequeña versus a proyectos que estamos hablando de los gigas, ¿no? Que lo cual es cierto en el sentido de que puede parecer ahí que hay una diferencia, pero la realidad es que en términos reales, en términos del conocimiento que se tiene hoy en día en nivel local, en lo que es en el desarrollo de estos equipos, no se llega a pasar los pares de kilovatios de potencia. Entonces, es bastante ambicioso poder alcanzar un prototipo de 1 megavatio de potencia que va a permitir justamente viabilizar los primeros tipos de proyectos pilotos para ir ganando experiencia justamente con hidrógeno. Y en segunda instancia también pensar que la tecnología de electrólisis es una tecnología modular y que también va a permitir, ¿por qué no?, en un futuro algún posible escalado de potencia. Nosotros el proyecto lo estamos pensando en líneas muy generales y para hacerlo muy de forma resumida en términos de la presentación, en 3 fases. La primera fase estamos hablando de una biselda y una estación de testeo, donde aquí la biselda, si bien nosotros estamos hablando por ahora de una baja potencia en el sentido de que no vamos a tener todavía muchos electrodos, estamos hablando de unas tapas y un electrodo, estamos hablando ya de una pieza, de un dispositivo grande, de unos 80 centímetros de diámetro, que el principal objetivo o desafío que tenemos en esta primera fase es probar o testear que los diseños que realizamos y que la selección de materiales efectuada sea la adecuada para las prestaciones que se requieren del prototipo. En la segunda instancia ya sí tenemos un escalado en potencia, que lo que hacemos es agregarle más capas entre lo que hay en las tapas, es decir, agregamos electrodos, y más o menos si llegamos a un stack de 45 electrodos, podemos llegar a un prototipo de stack de 200 kilovatios de potencia. Y finalmente, poder llegar al producto final o al norte que tenemos es hacer un arreglo de estos 6 stacks de potencia, de 45 electrodos y poder superar el megavatio de potencia, en donde uno de los tantos desafíos que nos vamos a tener que enfrentar en ese momento va a ser también una ingeniería de producto que permita un producto compacto junto con su balance de planta para que sea de una instalación accesible. En líneas generales, ¿cómo está ordenado el equipo de trabajo? Nosotros no estamos trabajando solo en ITEC, estamos asociados con diferentes institutos de investigación de Argentina. Y estos institutos también vale destacar que se encuentran distribuidos en diferentes provincias de Argentina, lo cual le da también un carácter bastante de federalismo al proyecto como tal. Tenemos nuestras reuniones virtuales que son bastante frecuentes y luego también hacemos reuniones presenciales con cierta periodicidad también para poder tener una actualización total del proyecto como una. Desde YPF Tecnología somos la columna vertebral de este proyecto, no solamente porque estamos con el gerenciamiento del mismo, hacemos el relacionamiento con proveedores y con aliados estratégicos, sino que también intervenimos en las diferentes áreas de trabajo que tenemos vinculadas para el desarrollo del proyecto. Por un lado, tenemos una parte muy fuerte en lo que es modelado computacional, tanto del stack como del balance de planta. Por otro lado, estamos desarrollando los materiales que tenemos que incorporar en el electrodo. Luego tenemos que diseñar y desarrollar el stack en sí mismo con su balance de planta, construirlo, hacer esas piezas, enviarlas a construir, ensamblarlas, testearlo. Y finalmente, también tenemos que todo esto orquestarlo con un sistema de control que permita una operación eficiente en primer lugar también y, sobre todo, segura. Hoy en día somos más de 30 investigadores y técnicos que estamos vinculados al proyecto de forma directa, más todos los equipos de soporte que cuenta cada empresa u organismo que nos ayuda a viabilizar el proyecto. Con respecto a la fase 1, que es la que nos encontramos actualmente, ya tenemos un primer diseño de esta biselda, ya estamos enviando a construir las piezas para justamente hacer el ensamblado de la misma. Como les comentaba, la mayoría de los insumos son insumos que se encuentran en la industria local. a excepción de la membrana de zircon, la cual debe ser importada. Y otra cosa que quisiera destacar, que no nos parece para nada menor, en compañía junto con el desarrollo de esta celda electroquímica, esta bicelda electroquímica, estamos haciendo una estación de testeo. Hay una facilidad, hay una parte de una planta piloto en particular de ITEC que le estamos haciendo todas las adecuaciones para que se opere con hidrógeno en esa facilidad, y que contar también que hoy en día no existe una estación de testeo para estas potencias y para estas dimensiones, va a permitir este mismo proyecto que salgan versiones B, versiones C, donde uno vaya mejorando, vaya haciendo otro tipo de tecnologías de electrolizadores, y también futuros proyectos que surjan a raíz se van a poder testear y se van a poder evaluar dentro de esta estación de testeo. También, como les comentaba, dentro de esta primera fase del proyecto, se están haciendo diferentes simulaciones. Nosotros tenemos que validar que mecánicamente los materiales van a soportar las condiciones de presión y temperatura en las que estamos trabajando, que vamos a poder garantizar una hermeticidad de nuestro prototipo. Y por supuesto, nosotros lo que necesitamos es que tengamos una muy buena distribución en términos de cómo va el electrolito y cómo se generan estos gases dentro del electrolizador. Tenemos un desarrollo en términos de materiales. Hoy en día estamos trabajando en particular con materiales niquelados, que la idea es obtener electrodos que me generen un área activa para poder separar la molécula del agua en hidrógeno y oxígeno con la eficiencia que se requiere para este tipo de dispositivos. Finalmente, con lo que nos gustaría un poco concluir o que nos llevemos un poco del mensaje, en primer lugar, si bien nuestro norte, nuestro objetivo está en llegar al electrolizador del megavatio de potencia, en el medio vamos a ir desarrollando prototipos los cuales ya hemos visto que tienen aplicación en el mercado, ya hemos visto que tienen aplicación, muchas empresas se han acercado y se nos han comentado que les serviría diferentes escalas de electrolizadores. Entonces, llegar al megavatio es el norte, es el camino, es el punto final del recorrido, pero estamos en el medio desarrollando una familia de productos que tienen potencialidad para ser transferidos tecnológicamente, sobre todo teniendo en cuenta, como les decía al principio, que la electrólisis es una tecnología modular. Entonces vamos a poder hacer arreglos de diferentes prototipos o diferentes productos para las diferentes aplicaciones que se requieran en función del usuario que esté interesado. Y finalmente, nos gusta también pensar, o nos gusta destacar, que esto va a generar, más que hablar de una cadena de valor, nos gusta un poco mencionar una matriz de valor, porque en primera instancia tenemos una cadena de valor asociada a los insumos y servicios que se requieren para la producción de electrolizadores. Pero con el desarrollo de electrolizadores de alta potencia, vamos a poder también tener disponibilidad de los equipos con una mayor agilidad, y eso viabilizar justamente primeros proyectos pilotos que impulsen la economía del hidrógeno en el país. Muchas gracias.
Muy bien. Excelente presentación, Ezequiel, muchas gracias. La verdad es que sorprende ver cómo ITEC ha venido avanzando en este proyecto piloto. La verdad es que Argentina tiene un currículum muy grande en desarrollo tecnológico. Solo podemos, por ejemplo, mencionar el desarrollo de energía nuclear, es fantástico, ¿no? De lujo. Y entonces creo que van a ser exitosos también en esta empresa, ¿no? Por cierto, te robaste la pregunta que quería hacerte sobre el consorcio, ¿no? De hidrógeno. Ustedes han venido liderando este consorcio, nosotros somos parte del mismo. Se ha ido creando todo un ecosistema en Argentina alrededor de este consorcio y en torno al tema del hidrógeno bajo en carbono. Así que también felicitaciones por ese trabajo. Y bueno, creo que estamos llegando al final del panel. Me gustaría solo girar un espacio de algunas preguntas que puedan tener los presentes aquí o virtuales. Sin embargo, no me gustaría cerrar sin hacer una pregunta que creo que es muy relevante. Carol mentioned that the low carbon hydrogen price is one of the barriers, no? Market is facing to grow with this this kind of production. No? I think Jeffrey and Carol could comment from the global perspective, no, how the policies, no, framework policies, are impacting the selection of the technologies in the low carbon hydrogen. No, perhaps Jeff first, then Carol, and then we can move certainly to our regional team.
Sure, I can start. So the United States actually has, very clear policies in place right now for incentivizing clean hydrogen production. It's a tax credit that's called 45V, and it ranges, up to $3 per kilogram of hydrogen being produced, and it's again based on carbon intensity. So to get the highest, absolute highest incentive framework, the easiest way to think about it is I think it's less than 0.4 kilograms of CO2 per kilogram of hydrogen. Very easy to sort of connect the dots and see green hydrogen as the way to get there. But you can also qualify for other incentives, with a slightly less attractive carbon intensity, but that still make really positive economics doing blue hydrogen production, or considering the use of some type of renewable feedstock to reduce the carbon intensity. So with that said, the US policy is actually incentivizing hydrogen production as opposed to penalizing, anyone for any type of CO2 emissions. As I kind of mentioned in our ExxonMobil case study, it's really driving the behavior to lower the carbon intensity. And so that's where we have seen that preference to really focus on pre-combustion carbon capture solutions and in the use of technology like the ATR, where you can capture the most of the CO2 in that pre-combustion case and at a very low carbon intensity. So that's where we see the industry, is really looking at, in response to that policy framework, driving down the carbon intensity and implementing integrated schemes, that include some gas recycle and the extraction of low carbon fuel streams to really make the lowest carbon intensity possible, to try to maximize the incentives available. So hopefully that was clear enough. And I guess in summary, it's carbon intensity is what's driving the technology selection, because the US, is sort of at the forefront in defining what these projects are looking right now from a policy perspective. I'll hand it over to Carol if she has anything else she wants to add related to that. So thanks.
Thanks, Jeff. Carol, any comment you would like to add?
No, I think Jeff summarized it well. In the US, we also have non kind of subsidies related incentives too. So we have hydrogen hub funding, where the Department of Energy has selected 6 hubs that are a combination of blue and green projects that are not just about hydrogen generation, but also building out the infrastructure too. So that's kind of sitting side by side on the support in the US. And then in Europe, I believe they're running auctions for I guess subsidies for 10 years on projects.
Muchas gracias, Carol. Bueno, César y Ezequiel, ¿cómo ven ustedes las políticas en Latinoamérica para impulsar el tema de hidrógeno bajo en carbono?
Gracias. En este momento creo que todos los gobiernos han tomado acciones alrededor de las políticas. Como bien Ezequiel mencionaba, en Argentina la hoja de ruta ya está allí, de igual forma en otros países de la región de igual manera. Y pues si vemos el último reporte de la Agencia Mundial de Energía, de la International Energy Agency, de la IEA, vemos cómo los recursos que América Latina tienen hoy consideran, pues no tan solamente el tener el ecosistema natural del recurso, sino las políticas de generación de este tipo de energías que pues liderado por algunas de nuestras naciones trabajando en ese sentido. Entonces, vamos en buen camino, se está acelerando ese motor, sería lo que de mi parte considero en esas estrategias de política, no tan solamente de exploración, explotación, producción, sino de desarrollo de competencias locales en la región de América Latina y el Caribe. Gracias.
Muy buen punto lo de la capital humano, ¿no, César? Muchas gracias por eso. Ezequiel, ¿algún comentario para agregar?
Sí, bastante en línea con lo que comentaba César, para ser honesto. Creo que es algo que está teniendo un avance muy rápido para el tiempo que consideramos que estamos hablando de esto, cómo nos estamos adaptando todos. Es clave que a nivel institucional se generen las hojas de ruta, es clave que a nivel, digamos, de cada lugar también se regule y que quede bien claro cuáles son un poco las diferentes formas de certificación también, porque sin lugar a dudas, Latinoamérica tiene una oportunidad muy grande en términos de lo que es ser proveedor de hidrógeno bajo en carbono y en términos de si vemos el balance mundial de los costos nivelados de hidrógeno, quiénes podrían llegar a ser proveedores y quiénes podrían ser off-takers. Entonces, es clave estar alineado a nivel internacional justamente con esos requerimientos para poder aprovechar esa oportunidad y el mercado que se nos presenta, siempre y cuando, como también comentaba César, vaya acompañado de un desarrollo local, ¿no? O sea, en términos de capacidades, en términos de industria, en términos de todas las aristas que hay que contemplar justamente con un desarrollo de la economía, que estamos a tiempo, porque si bien estábamos siendo rápido, creo que estamos a tiempo para poder hacerlo lo más prolijo que se pueda, ¿no?
Sí, muy buen punto también esto de las certificaciones, ¿no? Definitivamente creo que es un tema que se va a tocar mañana en otro panel. Muchas gracias por esos comentarios. Yo no sé si acá en la audiencia hay alguna otra pregunta que ustedes quieran hacerle a los panelistas. ¿Sí? Aquí viene una pregunta.
You mentioned in North America subsidies and tax credits. Would it work without them commercially?
I can I can answer that. I guess the simple answer, right, is no, until there's you know, a green premium sort of being applied in those market outlets, right? You know, it's a simple fact. You know, I think Carol outlined it pretty well. You know, the clean hydrogen is the more expensive hydrogen that can be produced today, right? So from a market perspective, it's not going to win out unless it's sort of helped along with a subsidy, or the selling price of that hydrogen, you know, is higher than the you know, conventional hydrogen. And at this point, you know, I don't think we see that market being fully developed, which is why you know, the hydrogen economy is sort of launching off of, you know, policy frameworks and subsidies to help enable that to happen. I'll let the other panelists comment if they see it differently.
Muy bien, muchas gracias. Veo aquí algunos rostros cansados, también allí los panelistas. Creo que estamos en el momento de cerrar este panel. Quiero agradecerles, Carol, Jeff, Ezequiel, César, por sus grandes presentaciones. Nos han enseñado también cómo ustedes desde la oferta están enfrentando este desafío del hidrógeno bajo en carbono. Vamos a seguir mañana con otros paneles de discusión. Bueno, muchas gracias también a todos los presentes y a quienes quedan todavía virtuales. Thank you very much.
Thank you. Gracias.
Thank you.
Gracias, thank you.
Thank
Bye
you.
bye.